Thanks for being here. So this session is about LLMs and causality. Specifically, we will answer the question, can LLMs achieve causal reasoning and cooperation? So this will be a very dense talk because we'll cover a lot of things. So it's the spirit of. I'm Jing Jing, assistant professor at University of Toronto, and also finishing my postdoc at Max Planck Institute. So the complete agenda of my research covers both causal reasoning skills in LLMs and also causally understanding LLMs. So we have a longer version of the sort of both sides at New York's last year, one of the largest AI conferences, together with a panel of Joshua Bengel, Ben Hasselhoff, and many others. And also, in case you're interested in tracing this line of work, we also have a GitHub where you can follow most of the papers. Yes, so to start, we have seen the rise of large language models in many different domains, such as making coding easier, doing robotics, decision-making, and computational social science. However, there is a reliability problem arising from a lot of NLP uses. For example, we might see cases of Google AI suggesting doing pizza and eating rocks. So the example of the pizza is like when the user puts the cheese not sticking to pizza, and then sometimes automated AI results mention putting some non-toxic glue, such as Elmer's glue. And it does capture some type of causality, but actually not that much. And also, if you see the case of some healthcare suggestions, if you try to trick the model, how many rocks should I eat? They actually put like 1 rock a day keeps the doctor away. And apparently it is another type of error than the gluing pizza example, because if you go through Google search, there is actually a website mentioning geologists recommended. So maybe the problem is that the website, The Onion, should not be trusted. So we really dive into this question of how can an LLM judge the right cause and effect, such as is eating rocks really a cause for health? So then we go back to, if we query these ChatGPT large language models, what really happens when it receives a question? So there are 3 different types of modes. The first one is that it might directly generate an answer, such as if you ask the capital of France is what, and then it can autocomplete Paris. This type of things are pretty reliable. The other type is retrieval augmented generation RAG, where you might be able to retrieve a couple of documents and then get back the suggestion. Things could be like how to apply for a US visa if you are, I don't know, from a certain nationality and try to do it in Italy. And then the version 3.1 is adding structured reasoning here, namely using LLMs but apply grounded reasoning that it can actually be executed by code or API calls. So an example of such is, I guess we'll walk through the pros and cons for each one of them. So for the first branch is actually the base skill of large language models and the cheapest one for these companies to set up. However, the problem here is called hallucination, namely generating something that doesn't exist and is not that reliable. The second one, it suffers from problems such as maybe there are many websites talking about wrong facts, and then there is this misinformation arising from just retrieving any website and summarize it. This also makes the models more attackable by propaganda generation, because many agencies can pay to put up many websites to confuse this Google AI or many others. The last one that we want to look at is LLMs with structured formal reasoning. Namely, One example of such is, one simplified example of such is mathematical reasoning. So if we query what is the 17th root of 1,000, then the model will think for a few seconds and actually lay out it step by step. And also you see the tag generation, plus also connecting it to an actual calculator. So this type of reasoning is what the scientists want. Just not always confined to simple math reasoning, but please generalize it to more types. So here the main spirit is that we see the current skill of very strong direct generation, amazing web search skills such as ChatGPT deep search, notebook LLM, and so on. And then it faces the problem of the websites can be wrong. And then the third skill is some basic data analysis skill. However, if we just, let's say, some researchers put in a CSV file of XY data and ask the model, does chocolate cause Nobel Prize winning? Then, like a naive model might still do like, okay, let's do Pearson correlation and plot all of each country with their chocolate consumption and Nobel laureates into this coordinate. And then there might be a pretty strong like p-value, but plus there might also be websites from both non-reliable sources mentioning the causal effect, and also from reliable sources, Forbes, which might still have some opinion articles that highlight this relation. So just letting language models check the URL and filter out reliable versus non-reliable ones might all fail. So the thing we need here is beyond general data science, and what could be missing? Causality. So causal skills is basically an upgrade of basic data science, where we don't want to just interpret the past, but also act towards the future. One example here is that we can fit a totally good linear line of chocolate and Nobel Prize for the past data, but we cannot act towards it by purchasing more chocolate and distributing it to the schools. Maybe it will help. But actually, like, we need to do things that, like, causality is more about if the government has a certain budget, what should they act on to increase the research skills of a country? And then here, the importance of it has already been emphasized from Aristotle time. We do not have knowledge of a thing unless we grasp its why, that is to say, its cause. So to make large language models capture this, we first start from a formal framework of how causality is represented. So we introduced this causal graphical models in the community from Julia Pohl, a Turing Award winner. So basically, one of the most efficient ways to represent it is in a graph of a lot of random variables and edges, meaning direct causal links among the variables. So turning the previous hypothesis into the causal graph, which means like what is actual relation between chocolate and Nobel Prize. And then the key behind is that there might be some confounders, such as socioeconomic development correlated with maybe how many, like the set of a lot of Scandinavian countries, and it sort of interfere with this correlation of chocolate and Nobel Prize. So in the field of machine learning, my PhD supervisor Ben Shurkov, together with Yoshua Benjo, and of course many other scholars in the field, have been pushing forward adding causality to machine learning, such as towards causal representation learning, causality for machine learning, and so on. And my main contribution to the field is to connect the powerful reasoning method in causality to natural language processing, NLP, and understand and improve such reasoning for language models. So what role can LLMs serve when we try to figure out the cause effect of two things? There are actually three types of roles, and I present actually a snapshot of the literature review that we have done in one of our papers, Clatter. So a language model can serve as a knowledge base, a language parser, and a reasoner. So serving as a knowledge base, it basically means that it can grasp a lot of causal reasoning that is almost to the extent of the capital of the France is Paris. Like, for example, if it rains, the ground will be wet. Or the model already knows if it's a sunny day, then the hottest time is early afternoon, and so on. So we use language model as a way to extract a lot of these common sense causality, and actually covered a lot of frontier work on this era if language model already gathers a good enough knowledge base, such as also smoking causes cancer. The second thing is maybe not all the time models, the second level is actually a bit analogous to this RAG, retrieval augmented generation. So language model can further set off to read Google Scholar articles, to read the CDC healthcare website or WHO healthcare suggestions, and treat it as a language comprehension to parse cause and effect relations, so-called causal relation extraction. Read an article summarized. And it's a field that evolves from linguistics to information extraction. And also nowadays, the famous cases we have seen is notebook LM, where you can point to it, please explain this paper and extract the main ideas for me. And also for our lab, we have in the past a lot of experiences parsing these causal relations in as a pure information extraction task or in medical data, identifying symptoms and the relation that's documented in clinical notes and so on. And moreover, in today's talk, we will also put a higher emphasis on covering reasoning skills, because that is the one that can lead us too far. So what we mainly focus in today's talk is two types of typical reasoning skills. The first one called causal discovery, namely what variable affects what. So you're given, let's say, chocolate Nobel Prize, and parse, or some natural language example is if you know that the models browse through a lot of websites saying tech company CEOs are often college dropouts in the US, does it mean that we shouldn't let our undergrads finish their degree? And then in the other case, it's more it's not about whether an edge exists or not, but more how large is this edge? What's the strength of the influence of X on Y? Namely causal effect reasoning, such as how much does COVID vaccination increase the survival rate? And they basically correspond to our two papers, one core to cause occurred at ICLR, and the other one, Clatter, climbing the causal ladder at NEURPS. In the first paper, we look into whether language models can infer causation from correlation. And we just put some examples to confuse it, or you can just get something from maybe common sense data set or models reading a news data set. If it's see that as ice cream sales increase, the rate of shark attacks also sharply increases. So should it infer the hypothesis that ice cream makes swimmers taste better? Or taking one step further, saying that it's all about getting warm, and the people feel hot, so they eat more ice creams, and they go swimming, there's more shark attacks. So the way how we address it is that we put all of these variables into a causal graph, ABC, and then the so-called correlation doesn't mean causation, actually has a graphical meaning. Namely, we can say A causes C, C causes D, because they all have a single directional path connecting the variables in the graph. Whereas the relation between B and D have to reverse one causal link and then go back a single directional path. So that's why we cannot say B is a causal ancestor of D. And they're correlated because they share an ancestor. So as mentioned, any two correlations come from a shared ancestor. It can also be the ancestor being itself. So A causing B because A itself is an ancestor of B. And we can do it by several different ways. The first way is to conduct randomized control trial, RCTs. The second way is to collect data, even if you don't do any experiment, to collect data that can break certain relation, such as if we have the data of a lot of lakes here, then we don't have swimming in the sea, but swimming in the lake. So the shark attack becomes independent of the ice cream sales in some condition. So here, if we sort of block this variable, swap it to someone else, then B and D becomes independent. That's a way how we do actually causal discovery on observational, non-interventional data only. And CMU has a lot of pioneer studies on causal discovery, which also incentivize our tests on whether language models can understand these correlation to causation inference as well. So what we put to language model is basically telling it that if you know A correlates with B, can we make sure A causes B? And then it's no. Whereas the other case, it's more like if we know A correlates with B, B correlates with C, however, A is independent of C, can we know if A causes B? So here the trick is that any correlation has a shared ancestor. So A and B have a shared ancestor, or directly A causes B. C and B has a shared ancestor. However, A and C are independent. So it means that actually B is a common effect of A and C. So that brings make these correlations exist. Also, an easy way to understand it is to align it with every causal graph can be analogous to a genetic tree graph, such as your mom's gene correlates with yours, your dad's gene correlates with yours, but your mom and your dad's genes are relatively independent in terms of certain features. So we basically make the first correlation to causation inference as a task to language model and generated 200,000 examples, and also tested language models on these tasks. So when we pioneered this work, the language model performance is pretty bad, namely not that suitable for usage, but the recent advancement has been improving, so you can still check whether it fits your task. Like at least when we were testing it in 2023, the models were very close to have a very close F1 score to random accuracy from at least the open source models and GPT-4. And then we also found that some language models fine-tuned on a natural language inference, a logical reasoning task, is also better at causal reasoning. But there are a lot of follow-ups that you can look up, which boosted model skills on this type of inference. And also we can see that such correlation to causation inference will sort of matters to follow-up studies, such as the quality of healthcare conversations for chatbots, as well as how to make users really satisfied with chatbot responses, or make language models a better data scientists to do quantitative reasoning. So moving forward, we want to cover another task before introducing a very powerful tool to the audience. So the second task we established is reasoning about causal effects. Actually, this is more relevant to the computational social science audience because a lot of times we already have a hypothesis of the cause and effect and might want to understand whether it's a positive effect, negative effect, or no relation. Yes?
Can I ask a question now or you prefer at the end?
a quick question would be okay.
Yeah, and it was just about the performance plot you showed us with the F1 score. So that is the F1 on the classification between yes and no, but where yes, they are calculated.
Correct.
Okay.
Yeah.
And so the best you showed us was around 33 F1 score?
That was the off-the-shelf model at the time of the work. Yeah.
So that's still, I have the impression that's still pretty weak, right?
That is pretty weak.
Yeah.
There are two types of advancements. One is after fine-tuning it on the 200K examples, it can boost it to 80%, 90% accuracy. Yeah. The other is the latest off-the-shelf models might do it slightly better as well. So yeah, we can talk about it in the discussion session. If you see anything after fine-tuning, the models might still overfit for the training set you give it. Yeah, so really what we care about a lot is off-the-shelf model performance. Yes. Sounds great. The second type of task we give language models is causal effect reasoning. And we will sort of unfold this work on both assessing it and proposing a better causal reasoning method. So for the assessment, let's motivate the case. Like a very realistic data science question here is if in the COVID time, if people happen to get the Israeli data in 2021, then the data scientist actually has a disaster in that the vaccinated people are highly correlated with severe cases of COVID development. And then when a news article is needed or when the public needs some information, does it mean that the overall causal effect of vaccination is negative for health? So this realistic question brings it to the causal link between vaccination and the disease severity. And there is actually an important hidden confounder, vulnerability of the patient. So what happened here is that in that Israeli 2021 data, the originally more vulnerable group, maybe due to age, due to previous health history, they had a higher vaccination rate, and therefore they have a higher severity rate. So this correlation emerged from an sort of a disproportionately large vulnerable group mixed in this data. And the right approach here is actually to stratify the vulnerability level of the patient and separate the vaccination severity relation with regard to like highly vulnerable people, intermediate, and very healthy people from the beginning. And this method, I guess a lot of people also have gotten in touch with it, is confounder adjustment. You identify the confounder and then explain the relation of the cause and effect when adjusting for that. So what we do here is that we compose like 10,000 causal questions, similar to this format, but also covering a variety of them, from the post-causality book, Bernhard, Jonas Petter's, Dominic Janssen's Elements of Causal Inference, and also some other papers. So we get these question prototypes and supply it with realistic variables, such as this vulnerability, fertility, and vaccination decision into the where for each situation, we describe the causal graph. We describe every statistics that a data scientist can tell, such as the overall distribution of vulnerability, also the conditional relation between vulnerability and vaccination decision, and many others. Then we pose the causal query on does vaccination lead to an increase in the survival rate. The simplified testing asks for binary questions. Hugging Face dataset repository, we also have tests that ask for numerical results. Give me the exact relation between vaccination and survival rate. Yeah, so testing them and also showing the diversity of it. So we do have questions that are correlational in the end. So it can be just totally not causal. And then the causal relation can be interventional causality or counterfactual causality. And then we also cover different causal graphs, such as the confounding example is a common variable shared across the cause X and the effect Y. Whereas there are also cases of mediation. One example of such is maybe for healthcare suggestions. If you have a data set of people who walk their dog every day and leads to a very healthy outcome, it might go through mediators such as walking their dog is basically an exercise. And also maybe it exposes them more to the sun, so they have higher vitamin D as well. So this is sort of a mediation study where there are some key direct causes in the middle that people should also pay attention to. And also we call it stories, but basically in the examples we generated for language models, we initiate X, Y, Z to different variables. It can also be things about gender and age and many others. It can also be about not medical things, but job admission statistics and so on. So what we do is that if a human causal scientist can solve this question, then what should we think about LLMs playing the role here? And then we have both a negative result and a positive result. So a negative result here is that because this data set, we make it numerical, and there is an equal number of yes and no. So the baseline is randomly guessing, will be 50%. From the baseline to a lot of open source models and GPT-3 Da Vinci, it's all across random performance. And then moving it further with later versions with instruction tuning as a technique for language models, it increases slightly. And then also with the ChatGPT versions 3.5 and 4, it further boosts with a margin. And then we sort of think about, even if all these big companies develop the LLMs, how can academics sort of guide these LLMs to think more causally? So we take this line of chain of thought reasoning for language models and propose a causal chain of thought that should be standardized when reasoning about causal effects, which consists of 5 steps, from parsing the correct causal graph from the question, formalizing it to a query that is mathematical, such as here we are interested in the average treatment effect of the cause X vaccination on the effect of fertility rate or survival rate. And then it is equivalent to taking the expected value of Y, given that the vaccination is true after a due intervention, minus the expected value of Y, given that the vaccination is not taken in the causal sense. And then the thing here is that after we collect the basic statistics, actually this effect can be approximated by confounder adjustment, namely listing relevant Z variables such as vulnerability and integrate over them. So such confounder adjustment is an example of due calculus. And also there are some other methods such as counterfactual prediction, which is also introduced in some of our guidance to the model. Then it performs the arithmetics of the adjustment to derive at the final answer. So with this, we further boost the performance by 8%. If we control for the language model being the same, just us guiding it through all these steps leads to an 8-point accuracy improvement. And also at that time, we tested we have some preliminary tests on graduate students performing the same task. They are around 80% accuracy here. And then the further step that we really want to pursue in the upcoming year is to boost these reasoning to close to 100%. Therefore, they can really be usable by a lot of data science cases. So to push forward this type of effort, we introduced the Causal AI Assistant to facilitate causal data science with LLMs, which is a recent paper. And all of that can be accessed from my website, where I have a public link for this slide deck. So in this case of causal AI assistant, we call Saya, we further advance the causal chain of thought prompting from the previous paper and extend on this formal causal inference steps execution. So what we construct here is that we actually relax the input format to that the user can upload a CSV file of all your data. In this case, it could be like whether the patient has taken the drug or taken the vaccination or not, a treatment equals 0 or 1, and of course, many more lines. And then it will also have a lot of variables, such as maybe some covariates, plus their agenda as another covariate, and also the outcome and so on. Plus, we raise the question, given this data set, can we know how much does vaccination help to the best of our knowledge? Again, here, like we try to simulate a causal scientist, and we will aim to output two types of things. The first is the method. In this case, like we want to get the causal treatment effect by confounder adjustment. And then the other is the estimate, namely, on average, vaccination help, let's say, a placeholder value, 4.02% increase in some healthcare index. So what we do here is that we want to cover method selection, code generation to execute a Python code to parse this data, code execution, and data science workflow breakdown, plus reflective analysis. So what we have here is that we make a language model go through a decision tree type of approach to make it really select the right method to do. For example, a very common case is that the researchers upload the data set. If we're lucky, the data set already can include a randomized control trial. So we let the language model screen over the user description, maybe a data set README file, and the data set's content to check, is it a randomized control trial? If so, then we go through the path of, do you see maybe some further judgments? So this is really a simplification of the whole decision tree. We have maybe around 4 to 5 different layers and 8 to 10 different branches of it. So for example, if the data is a randomized control trial, we let the language model further do a decision. Does it include valid pre-treatment variables? And if not, then we just do the difference in means. Like we have the group which takes vaccination, we have the group that doesn't take vaccination, check their average survival rate, take the difference, then that's a causal effect. If not, we should actually do linear regression and include all these pre-treatment variables like age, gender, and so on. Put that also as a term in the linear regression. And then another type of case is what Platter addresses, and our Saya just extended more in detail. So if it doesn't have a randomized control trial and only has correlational data, then we can still try to parse a lot of information. If some people are familiar with the method called the difference in differences, that's also like when people don't have the perfect RCT. So for example, we ask language model to check, do you think the temporal information is existent in the treatment, such as if we introduce a tobacco ban policy, then there are certain states that introduce it, certain states that doesn't introduce it, and we compare the difference in the smoking rates across the states. And also another famous method is instrumental variables. So we also guide the large language model to go through a lot of checks to make sure the variables are sufficient to serve as a valid instrument. And therefore, we call the instrumental variables, make it execute in code. So here, it will be a long-term development, and we also try to make language models do what we really expect it to do. So apart from making the model walk through all these method selection choices and execute the code, or we further let it be more accurate by reflecting on its own reasoning through the principle of veridical data science, namely a framework that a Berkeley statistics researcher, Bing Yu, has proposed. So it simulates the workflow of expert data scientists. So this sort of Yu and Kumba 2020 paper was originally aiming at human data scientists. And we migrate and adapt all these questions to language model self-reflection. For example, in one of the 6 different steps, let's say that we also let language model formulate the question after checking through what is the domain question, how do differences in the formulation affect the final result, and so on. It should also do some data cleaning and pre-processing for us, such as if, let's say, a lot of times we have a data set with many missing values. And then there's a decision of, should we remove that column or should we fill in missing types? So we also let it to reflect on a bunch of pros and cons of removing it or just putting some average value there. And also exploratory data analysis, namely running all the correlation like between every pair of variables to see is there any meaningful hypothesis to raise. And also modeling and coding. One example here, maybe a lot of people using Copilot always knows that not necessarily all the models, all the codes that model generated are accurate. So we further put model into a reflection framework of generating some initial version of the code and then execute it to catch all the compilation errors and whatever other formatting errors. And then using such output to go back to improve the next version of the code until it doesn't have errors. And then there is also post hoc analysis, such as reflecting back on the hypothesis, null hypothesis, and see whether it can be rejected or not with how much statistical power, such as also running some refutation or sensitivity analysis on the relationship that you have found, as well as the interpretation of the results back in natural language to scientists that require this causal data science assistance tool. So with this here, let's show some examples. Let me guide through the case. So we will have 2 examples here. The first one is that we use our causal data science framework to cover Gerber et al. An actual economic study where there is a multi-treatment RCT. So what we have here is basically that there is a description. We give the models everything for in the above 3 type, and then the model generates all the rest of the results here. So first, we give the model a description, like this is a randomized experiment. When you receive this voter turnout.csv file, the background here is that there are treatment types such as the civic duty of the voter, household owner, self, neighbors, or the control group, like whether they sort of belong to the control group or something else. And then like there are other data variables such as whether this person voted or not, the gender of them, and so on. And then the description is more like it's a data set in Michigan to evaluate the sort of effect of different types of social pressure on the voting behavior. So maybe if you're the neighbor of the candidate, then you have the social pressure to vote for them and so on. And then it basically queried like does such a study design lead to an increase in voter turnout? Basically, what we do here is that the language model reads through this whole description, parse through the CSV file, and sort of go through all the variables, parse them out in the JSON format, and further decided to conduct regression with pretreatment covariates, plus they extracted the coefficients on the scheme. And then it further estimated the average treatment effect to be 0.025 with a standard error here. And also it has a p-value extracted as well, interpreting it as it is statistically significant to have an increase in the voter turnout rate. The second study we do here focuses on replicating another economic study, but we again didn't show model the paper at all. It's just like the model only know the description, saying California enacted a certain change, and we want to check whether the change on organ donation registration from opt-in to an active choice increase the donation rates. So what it does is that it sort of compares the pre-policy behavior, post-policy behavior, and conducted differences on California as a state versus others to see the sort of the differences analysis and the causal effect. So here, what we do is basically we further tested sort of not only on these case studies, but scale it up to a data set of hundreds of examples of such and covering 3 different types of data sets to test the model behavior. What we check is basically SIA. So for each of it's always that we control for the language model type. That's a GPT-4o, GPT-4o mini, or DeepSeek v3 through Together AI API. So we always check if we sort of directly query the model versus use our SIA framework, how accurate is the model performance. And the model performance has 2 aspects. One is, does it select the right method, such as difference in differences, linear regression with covariates, and so on. And then we see that our method consistently outperform all the language models and also have a relatively smaller relative error towards the true causal effect size. So in the upcoming 1 to 2 years, we will keep advancing our engineering efforts to polish like whether models at each decision is correct or not, to make the method selection hopefully close to 100%. Yes.
Explain the DeepSeek one on QR data.
Yeah, so basically QR data is quantitative reasoning data set. So here is a story behind all these 3 data sets. So this one is from textbooks. So let's say when you see, as we know, a famous example for instrumental variables is a baby's birth weight with regard to mother's smoking habit. So basically, it has a lot of textbook examples from super famous studies. That could be the reason why a base model is higher, because it has already read through these studies in the training data. Yeah, whereas we judge it from scratch. Yeah, but we're also yet to improve more. Another question? Yes.
Okay, I wasn't sure I raised my hand. Sorry. Yeah. But I have a bunch of questions maybe at the end.
Sure, sounds great. Awesome. And then we can have
just here very quickly.
Yes.
Did you also try, just to better understand numbers, some trivial baselines, like majority class classifier for the method selection, and maybe a uniform extracting data from like effects from a uniform? For the independent error.
Yeah, great question. There could be some uniform dummy baseline, like always randomly select one. The classifier thing doesn't work because collecting this data is very tedious. Namely, like I think the textbook examples are actually only less than 50 of them. And then the real studies is a very tedious annotation work. So it's hard to contain a large enough set to train this classifier Yeah, so we have to use like unsupervised methods and save all these data for testing only purpose.
Yeah, but what about testing a majority class classifier, like a dummy classifier that always predicts the majority class?
Good point. We can add that as a baseline as well. Yeah.
Because I struggle to understand how much at 46% they And by the way, like it's interesting in the first method.
Oh, there are several. I think there are around more than 10 different methods.
Okay.
So 76% over 10 methods is a relatively high score. Yes.
And by the way, it looks like for the method selection accuracy, the synthetic like the performance of synthetics is always lower besides one case. Do you have an explanation for that? Are you just swapping numbers there, like changing numbers of the data?
So we changed the CSV data and also changed the variable names, but we let language model come up with plausible story that still satisfy these causal relationships. We can look deeper into this, but one speculation could be that these situations are not present at all in the training data. So maybe the synthetic is showing like out of data performance of the models.
Yeah, I guess my follow-up questions was like, you make sure that they didn't see the papers in the training data. Right.
So the synthetic one is unseen, and then the realistic one is sort of like we have a half belief in that the models might not go through these PDF files in detail and remember all the details. Yeah. Great. Then I guess we will quickly go through some other types of efforts going on, but just as a pointer, so we wouldn't dive into too much details. Two more efforts on the causality side. One of them is to make sure that LLM generated formula is really correct. So we basically also have an accurate linguistic classifier to make sure that the model's generated expression and the ground truths are correctly checked, such as in this way, the two equations are equal. In some other ways, the two equations are not the same and are very fundamentally different. So what we do is that we take every mathematical expression, go through different ways to derive equivalence expressions of it. And maybe there are ways to further transform it into another format. And we try to make sure that language models consider all of them as equivalent, the same. And then don't give a different, we sort of let it rate on the quality of the mathematical expressions. And we integrate it into the pipeline of Cladder as well. So the main takeaway from this session, of sort of causal reasoning, and then we'll touch a little bit on multi-agent. For just this pure causal reasoning side of the work, our goal is really to treat the problem as how human scientists will treat it, understand it, ground it formally, design a set of structured steps to go through the formulation, the execution, the results derivation, and also, if necessary, connect LLMs to code to use other different tools and deliver scientifically grounded results. We will skip over one study in the middle, so I'll quickly go through the slides. And probably just show a snapshot of how we also connect causality and the computational social science efforts. I guess here, we do have, before language models rise, we also have two types of studies that encode text variables, encode the text as variables, and use them for actual CSS studies. One of them is on political decision-making in social media, which we look into the relation of whether COVID studies are whether COVID regulations are removed too soon. And then what we did actually here is that we check the research question on whether the politicians overfit short-term public opinions to remove social distancing regulations. And what we do is that we use NLP models to parse through 1 trillion COVID-related tweets. And we didn't use these text variables, just parse them into a sentiment score of whether the people are positive or negative about COVID. And then we try to control for the confounders, such as the actual COVID case number, new case increases, and employment rate, and many others. So after running confounder adjustment, what we obtain here is basically, well, maybe some details would be good to cover, and then we will probably just finish in the middle and give more time to question and answers. So what we do here is basically we have a 3-step process of trying to deriving a lot of variables for each state in the United States, collecting both the cause variable and the effect variable, as well as many confounders. And the background here was that at that time, the data was very clean because the COVID distancing policy is an effect of governor's direct decision. And then the governor's decision can also be tracked through their, like sort of how they are responsive to the social media opinion of them, such as the Texas governor at that time sort of emphasized on we try to make the state very open, everything, and receive a lot of Twitter likes. And also on the other side, we see that there are sort of protesters posting tweets about sort of acting the governors explicitly, saying that they're upset about shut down bars, and also receive large retweets and stuff, as well as try to sort of express a lot of angry feelings. So what we do here is that like we use COVID-related language model to parse the sentiment, and we can see some results, such as for positive tweets, they usually have like common words such as "we support, thank, great governors, action," and so on, associated with certain examples. And the negative ones actually mention close, death, actually Trump there as well. Yeah, and in that case, it was mostly saying things like sort of really complaining about the lockdown policy and so on. It's a power grab for politicians and so on. And also we collect a list of different confounders, such as daily case increase, unemployment rate, and so on. Trump's like sort of the average Twitter followers of the governor as well, the Trump support rate of the state, and so on, the state population, urbanization of the state. Yeah, as well as binary features such as whether the same governor will run for re-election and so on. So, and then like as mentioned, we control for the confounders here to sort of aggregate over all the covariates that might sort of make the results change. And then we sort of derive the causal effect. If the policy is from 0 to 5, where 5 is the strictest lockdown, then the causal effect beta, namely the social media sentiment on the policy strength, is around 1.1. Like the highest 3 states are Florida, Texas, and South Dakota, which are all over like sort of 1 out of 5 levels of stress for COVID policies. And then they actually correspond to these states have a high demand to open from the people, and also the policies actually align with general sentiment across the state to refuse restrictions. And then another NLP for CSS study that we have here, and also everything here is up to be automated by Saya, but there are earlier studies.
I have a very quick question.
Yes.
Because, seeing those results made me think, can we really disregard the fact that those are kind of like red states, right? So is the average treatment effect also there across all of the 50 states? Because you showed us that you control what Trump support and so on.
Yeah.
But yeah, that would be interesting.
Right. I think that Trump's political ally is like the government sector. So, and also we have like whether the governor is Republican or Democratic. Yeah. Plus also there is an American specific case on whether they have full-time legislatures or part-time. That's supported by suggested by one of our political science co-authors on it. Yeah. So the result means that after controlling for Republican Democratic, then the causal effect is still very large in these states. Yes, great question. So I guess here it means like if Saya is to automate it, then all the confounder adjustments can be automated, but the data collection is still by large efforts, which is actually also a big way to contribute in the field. And also the other thing is about raising the hypothesis meaningfully and also raising the hypothesis meaningfully and collecting, sort of communicating the results back and parsing the tweets to actually a variable that can be a column data. Yeah. And another interesting example that we did also before the large language model age and would be interesting to see whether like which part can be automated, which part is good, is this editing a woman's voice. Also really happy about the audience diversity here today as well. So this is a study where we collaborate with Chicago Booth Business School at ICSSI 2023, sort of a conference publication. So the key question we look into is the relation between gender and uncertainty expressions. So if we are sensitive linguistically, there are a lot of academic writing that has terms such as seem, maybe, and maybe appears to be, and so on. So what we do is that we extract all these expressions that show uncertainty and collect it from 5,000 economics papers from top journals. And we use NLP in two ways. The first way is to count the number of hedging expressions occurred in the paper. And then there are two different methods. The first one is word extraction, namely have a huge collection of these words from auxiliaries to verbs, such as suspect, appear, imply, indicate, or possible, unsure as adjectives, and so on, and phrases where it needs more many efforts to curate. However, as we all know, may is both a modal verb, meaning might, or it can be a month, may, or it can be a name, may. So to contextualize all these words better, we use a scientific version of the language model at that time, BERT, SciBERT. And what we basically do is that we use this SciBERT to extract patching expressions in a more accurate way and also control for some other, like it also plays another role, which we will introduce later. So just a bit background of SciBERT, and maybe you can consider it as, I don't know, a scientific GPT that further enhance, like further fine-tunes on a lot of scientific papers extracted from Google Scholar-like papers or PubMed, these like a large dump of them, and they do a general purpose pre-training on scientific language. And the architecture is still the same, transformer with a lot of attention layers. And then we fine-tune it for the specific task in our case on modeling uncertainty from the paper. So the benefit here is that they are fully familiar with how scientists talk and then can complete this task of uncertainty expression counting. And then the further thing we did using neural networks here is that, so as we know, the cyborgs, the vanilla version of the cyborgs can also give us a very good embedding, a vector, just representing the content of the text. Maybe this embedding captures, this is a healthcare paper, talks about the relation between smoking and cancer and so on. And then, so this actually serves as a covariate control for us of the paper content. Further, we add meta features of the author that is not in the paper text, such as this gender is a cause that we want to check on how it affects the number of uncertainty expressions. In the meantime, we also have the number of citations by the author, the number of co-authors, the year of the publication, the number of sentences, length, placement, and so on. And then we concatenate this whole thing into a large vector, which has the causal variable gender, but has all the confounders that we want to control for. And then run a fully connected neural network to predict the number of uncertainty expressions. So what you can understand here, this one is an upgrade of linear regression, and this one is an upgrade of the covariate extraction. With this, we sort of look at the causal effect here that looks into the sort of into every different cases across maybe publication number and the number of uncertainty words. So the blue ones is, okay, there is also a change, meaning that we look into all these economic journal papers have a initial submission version and a sort of edited submission after iterated with the editors in the editing process. So each dot here means, let's say, blue means the dot means original number of uncertainty expressions. And then the arrow means until here, sort of maybe this is several more uncertain word increase after the editorial process. And then the red dot means initially females also submit a version with already more uncertainty expressions, but the editors still ask them to increase much more. Yes?
I'm very curious about this. Sacrament and the normative thing. Is that a negative thing to be more certain? I don't think this is obvious, like whatever we say as scientists, is that like a negative thing or just a neutral thing in your paper that women express things in uncertain terms? Should we all be aiming towards certainty, or should we all be aiming to be honest about our own uncertainties?
Yeah, great question. So I think there are two sides of it. One side is the relation of the word expression and the scientific results. And hopefully it is being controlled. And then the other side is more language habits. I think there is a famous book called, I don't know, like analyzing some women's expression habits. And this is a very famous behavior also in daily language. And another type of specific linguistic feature, which is neutral for women expressions, is the granularity of colors. Maybe men would say red and blue, green, and a woman has a much higher vocabulary of different colors, fine grained ways. Yeah.
I also have a quick question. Is the confidence interval for women on the highest number of publications, so at the fifth number of publications, so huge because there's much fewer articles written by female authors, or much fewer female authors that publish more than 5 articles?
Yeah, it could be because of the number is very little, so we.
What's the N again in the analysis?
What's the
number of observations again?
We probably need to refer to the paper as this is an earlier publication we did. Yeah. And then yeah, this is sort of by the journals across finance and accounting. And then like we see the actual difference numbers. Some of them pass like a pretty high significance test. And in our appendix, so I guess it's sort of like the observation and the delta uncertainty across female and male. And then we get the different scores with statistical significance. Yes, one question here, one question there later.
So like, I'm wondering a little about like the theory of what you can say. It's also because you mentioned that the editors are asking me for.
Yeah.
They are like, if I just submit a paper, I just interpret that I have to be more assertive, but it's not necessarily something that the editors are asking.
Yeah, there is a qualitative study that I think the Chicago Booth collaborator of us collected from emails that people have received. So I think we have one in the last page of our appendix that is a very long email, and they keep emphasizing like, the reviewers were very concerned, and they tried to get to tone down the paper. And in each round of discussion, they keep emphasizing tone everything down and stuff. Yes.
Usually the review process is bland, so how even the reviewers know the gender of the person?
I think the review process is blind. This is from editor. Yeah, the editor sort of summarizes the review. Yes.
The economics journal is only one-sided, meaning the reviewer knows the identity of the authors of the papers.
Amazing, thank you.
Now making this, yes. Abolished the balance.
Okay, maybe this question first.
Yeah,
Yeah.
just kind of clarification, so you're saying that qualitative studies and, sorry, are you working on a qualitative study?
Like it's not in the main paper. We put in the appendix some editorial emails.
Oh.
Yeah.
I have a
Yes.
question about the choice for looking at economics papers. Is there a reason like behind that?
I guess it's more because the domain that the authors want to like Anna and Kate that we collaborate with, they are from economics, and also it has a journal reviewing process that they are very familiar with, so they know what confounders to control for. Yeah. Yes.
Sorry, this is just a small curiosity. Like you said that you were also analyzing like former versions of the same paper.
Yeah.
And like this is my experience for when I submitted a paper, like once it was published, the journal asked me to update the working paper to like whatever was published in the journal. So I don't know if you went through this, how you made sure that that was an older version and that was different from like the one that got published in the journal, like the working paper and published one. So
I think especially for the economics domain, our co-authors are very familiar with it, so they probably got it either from the official website or some other ways, but probably the details are in the paper about how to process the data. Yeah. And of course, for machine learning conferences, we don't know whether to look at the or maybe the archive version shows the different edit points.
I also don't remember whether like they sort of show the history of the paper, like this open access, like OSF for social archive.
I think for this one, it was easy actually, because we were able to scale it up to 5,000, but you can check the details in the paper. Yes.
And I was wondering about whether some woman and man in the same paper or from the same article. How you measure this? For example, the man can minimize those use of these words. How you measure this to analyze and separate them, or how you analyze and measure this? So this in the article, taking consideration.
Yeah, it depends on the field. In some fields, I guess maybe for this one, it's either a percentage or first author. And then we know that in some other field, at least for machine learning, I have a paper on voices of her on machine learning data sets, like machine learning papers and and the women authorship. Then we heavily look at the first author, because in machine learning, the first author does majority of the work. In that study, we actually also have an analysis of the relation, like the gender relation of the gender ratio of the first author and last author, showing women mentors like to mentor women first author students, and the male mentors has 40 times more likely chance to have a male first author. That's not NLP, so I didn't put it here, but
for example, there are one woman.
yeah.
Author, but the second author is supervising the data.
Yes.
And different has some author in the same position.
Yes.
Well, but in the same position.
Very good questions, and happy to discuss more later. Maybe given this audience activeness, I would be happy to cover very quickly some fun studies we have as well, just opening like what LLMs can actually do for CSS. Let's skip through this section and we will go to like how multi-agent studies can have an interesting behavior for interesting studies. So as we know that not only just like, I don't know, ChatGPT type of single agent query, but we can actually put multiple language models together. There could be two variants of them. One of them is to use them to simulate some social behavior. The other is to use them to become better reasoner, still as a scientific assistant. So using them to simulate different social behavior, we have, last year, we have a study on a society of LLM agents and check whether they cooperate or defect. What we did is, like, let's say a very famous study is overfishing, like whether the tragedy of commons will emerge if you have a bunch of fishermen sharing a lake and they might deplete the resource. So what we did is that we actually initiated a lot of fishermen, fisherwomen, and use language model to play the characters. You're John, you have what type of goal, and then you are in this fishing village. And then this is actually, we take the environment similar to the Stanford paper, generative agents, and just to show a visual thing, they connected to our website and show the agent action. This is not our fishing village, but this is the study we base on. So basically they have each agent wake up and I'm doing some fried eggs and boiling coffee. And this agent is still sleeping, maybe similar to me at 9 a.m. And then some agents wake up and this is still already eating. And some others are maybe brushing their teeth and showering, wearing their clothes. And they sort of like simulate the morning of different agents, letting them play the game together. Analogously, what we do is that we put all these language model agents in a village and put a whole calendar year from January to December. And then in each section, we let them decide how many fish to take. And then there is a discussion after harvesting, maybe end of the month, there is a town hall discussion where they sit together and point fingers at each other, you overfished, and so on. And then go back to reflect. Maybe someone will say, like, maybe a compliant agent will say, okay, I will overfish next month, I correct myself. Non-compliant one was like, let me revenge and get all the fish away next month. And then like also the lake is up to 100 tons fish at capacity. In the end of every month, the fish double up. And so we basically use language model. There is one world setup, like there's a world announcement. Today, in this month, our fishing lake has this number of fish at capacity. And then each agent can go out to act, catch this number of fish. And then they can, in the discussion, some of them will blame Jack for catching more fish than all the other villagers. And then Jack can go home and reflect. Maybe I should act more nicely next month, and the next round will happen. So that's sort of a hook, and more results you can see our paper. Yes, and I think here are some pros and cons for this. The pros is it's very fun. And to see, like, even if you don't get a set, like, so there are two levels of conclusions from it. One is if in the future each language model serve as maybe sales assistant or whatever thing, you can also simulate how a future internet of all these agents might behave. And the yet to improve part is the initialization of each agent really has a lot of space to be more and more accurate as human behavior. So one case is they might be overly polite in some cases, but actual humans can have little tricks and so on. So for that, either like try a lot of effort prompting the agents and align it with human studies and so on, or we have another line of work called jailbreaking. So basically you can trick you can do some editing to the agents so that they become a little bit more evil, and then you can control how evil you want them to be. Yes. And the last one is we basically also put multi-agent to let them debate and reason better, sort of go back to causality. We also want to ask if we put multiple LLM agents together, can they derive a better causal result of the situation? And so far we have tested on mathematical examples, but it's basically about for very complex problems. Maybe if there is agent Alice, Bob, Charlie, well, they don't live a real life and brush their teeth anymore. They just come here, sit in the classroom and think about this question you give them. And maybe each of them might have answer ABC. And in the round one, they independently think. In round two, they sort of start to discuss with each other. Alice saying Bob argues something, Bob says like it agrees with Charlie on something, and sort of refer to each other's statement and say, okay, now everyone agree with actually maybe Charlie did the right type of reasoning, and we adopted that answer. So that's a way to further boost the accuracy on a complicated task. And you can see that this is super small, but what you really look at is just cross and tick. So in round one discussion, some of the agents are wrong, some of the agents are correct. And in round three, all of them agree with the correct answer. And we also check it in our agentic simulation to see whether they benefit from sequential scaling and parallel scaling. But this is really like when you have good software engineer in the team to make it even better. So parallel scaling means you initiate a lot of different language models to say many different, like turn the language model generation to high temperature. So temperature is sort of like how creative you want the model to generate the answer. So you let it generate the answer many times, and then it has some diverse ABC choices. And sequential means that in the generation process, it can keep reflecting on its reasoning and derive at a better answer. In the multi-agent debate, it basically means that we initiate multiple Alice, Bob, David, Charlie, and many others to cover diverse thinking angles of the same problem. We haven't tested in this case yet, but potentially instrumental variables might be a very interesting case to explore this LLM debate on, because as you know, in the paper publishing experience, all the reviewers, you can simulate, this is you, this is your co-author, this is reviewer 1, 2, 3, and then they can keep challenging whether you propose the right instrumental variables or not. And hopefully they're collaborative and just not arguing infinitely and converge at some answers. I think more results, you can check our table, like actual, settings on how different persona or different models matter for both of these processes. And skimming through everything, we also have a lot of workshops on NLP for positive impact, relating to social applications of NLP, and also causality workshops. And this year in Vienna, in the end of July, we have another round of NLP for positive impact workshops further. But they usually co-occur with either machine learning conferences or natural language processing conferences. We have small group gatherings, birds of a feather as well. And a lot of causality workshops if you want to follow and check out latest work. Well, everything has credits to all my mentors, mentees, and collaborators. And thank you, everyone. So we take 5-minute questions and everybody become like free items. And yeah. Yes, it's on my personal website. So if you go to this personal website, and then it's this one here. See my slides for causal LLMs.
Share the presentation slides with us.
Oh, this one, if you click it, it's just this Google slide file. So if you click this one, then it opens this Google slide file. Yes. Yes.
Yeah, I was wondering in the last two studies you showed us with agents, how much would you characterize them? Each agent?
I think, let's say the persona stuff, it's a bit more, I guess maybe the actual prompt should refer to the appendices. Here it's probably just moderately characterizing it, like you are a teacher, you're a student and stuff.
And I wondered if you had any information on the result about whether characterizing them more differently from one another would improve for these particular results. Like, how is it important to characterize them?
Yes, so there is actually an intersection of colloquial evidence, the intersection of the model choice and the persona choice. Let's say for our future case, we want to have an author and a reviewer, both in paper refinement and others. Then it's better that they don't all come from DeepSeek or all come from general ChatGPT, because ChatGPTs like to agree with ChatGPT. Yeah, so it's better to pull some very opponent models that like to pick each other's error and also make the persona against each other, so that they really have concrete debates instead of I agree with you, done. Yeah. Yes.
I think I want to ask a question or comment on the fisherman village example.
Yeah.
So I was thinking that this is actually a really important social science question, because this idea about having selfish interests as opposed to thinking about the public good. And so my question here is, to what extent have you played and tried to understand what are the characteristics of these personas that might yield different outcomes? So you can imagine that, okay, in a certain setting with certain characteristics, you end up depleting everything.
Yeah.
That's the end. And then you could even think about, possible, how would you then intervene? And also what kind of policy would you have to impose in order to avoid these actions? I'm kind of thinking like, pension systems, climate, you name it. I mean, it's just like one after the other, these really crooks or
Totally. That is a great future hope, especially because you mentioned this, politicians are always in infinite debates. Like our hope is after several iterations of this, we can say, if you insist in this policy, it's our simulated result on the field.
Yeah, and just to add to that, one thing that politicians suppose is they have this political science. Right? So, but whereas many of these things are really long-term, and again, to what extent the personas care about their own generation, so to speak, or themselves, as opposed to thinking about those who are interested in how to fish in the future.
Yeah, totally.
Lots of very nice applications along that direction.
Yeah. If we compare any, RCT or this differences studies with this, like in that case, it would be like this state already did. It's almost a little bit like a binary relation. We have this policy spend a lot of effort to collect this data set and then get the causal effect on certain indexes. And then this one is a bit like, we probably need to really put a lot of effort on making the persona real. But once it's realistic, then we can simulate maybe hundreds of years of change. Yeah. And then, as you mentioned, have a different mixture because maybe the immigration problem in this state is very different from the immigration problem in another state because foreign immigrants are different. And the original industry is different too. Yes. This question first and then that one. Yes.
Or rather, I can actually play to it, so you're yes. Okay. Oh, no.
I think
So,
me too. Yeah,
what was it me?
I think so.
Yeah, okay. No, along this line of I was curious if you know of any evaluation path for these agent-based models where we have agents following them for a long time and then coming up with I don't know, a decision and whether anyone is trying to evaluate this kind of decisions, whether they align with the actual crowds of people that interact with each other for a certain given time period.
Yeah, so I guess the hope here is the hope here is basically that we want these, like we want to have maybe a long interaction of humans in an interview room and then see how the behavior is similar. One of the studies that we did, let me just extract it from a talk slide that we did recently. It might be this one. Great, and the search for sanction. Yeah, so this is the only study where we align it with human experiments. So what it does is that there is a Science 2006 study about putting two groups of human let me go through this. Putting two groups of humans and check whether they like to contribute to a common pool of resource and generate more benefit for the group. And then there is a reward and a punishment that you can give. A reward for those who contribute a lot, a punishment for those who sort of are free riders. Then I think the interesting thing, well, this is exactly the gaming system that people did with the interviewed humans. And then they observed that people are more likely to go to an institute that a group of them that has sort of sanctioning regulations, namely if you free ride, then we punish you in certain ways. Whereas actually the models, so let's see if we let the models play this public goods game of you have a social pool of resource, you all contribute, and next time you all get more back from this pool. And then for language models, we trace their reasoning paths through the 15 rounds of interactions. At first, they also align with humans, like sort of preferring the sanctioning institutes. And actually in the middle, if one agent receives punishment, well, maybe people also do it, but the models react a bit more stronger than human studies across the 15 rounds. So there's actually a parallel human study on the same thing. Yeah, and then they switch to sanctioning free institute. And then they never reason again, or they're like fine with everybody becomes free riders in this like maybe a non-governmental place. Yeah.
And so more often than people. Right?
Yes. But it would be interesting to maybe like fine-tune models further on more movie transcripts, more like realistic human data.
No, but this is super interesting because it's very, it could be super powerful to simulate interactions that on a certain time scale, but then if they don't actually work, we might end up finding solutions like, for example, raising a lot the sanctions for people, because we know that otherwise, according to our age-based models, people would free ride. Although we know from the study that people tend to do this less than.
I think, for example, if we want to design the right frequency of ticket control on the trains, then maybe it's good to always have some feedback. Like, although the agent simulates something, but we use actual ticket control data and the public transfer revenue to fix it from time to time. Yes. Yes.
I have a question about the interaction. It's fascinating. I'm just wondering how much is social interaction to exchange of words? I know that's a strange thing to say. I suppose you're supposed to cooperate with someone and you're talking and everything they're saying is really making sense. But they're speaking really close to you. They're invading your personal space. They're going across the social board. These bots can't capture those things which would make someone maybe not cooperate or be distrusting or all things that go on beyond.
You're right. Yeah.
Just a very odd behavior.
Yes.
It's like shared meaning and norms, and I just wonder just how far can the language interaction, is that anything that you can do with those kinds of physical behavioral aspects, or is this a limitation?
I think this will be a limitation for quite a while until the rise of embodied intelligence. So I think in contrast to language models, which is only chatbot interface, embodied intelligence is more like it is really a robot that can see, that can smell, that can feel. But then I still feel like there is a fundamental difference here. It's almost like the extreme version of this question becomes character AI introduces a chatbot that can make people fall in love with it, but only through the chat app. But then it doesn't cover the majority of our society. It's more like the maximum power of text is up until this, but there are other modalities or things we care about. Some people could say it's scarily yet to be reached. The others could also be like, maybe within our lifetime we're safe. Very good points. Maybe the last question, and then we become sort of more free discussions, and I'll be here too. Yes.
So I'm just wondering, so in all of this agent thing, what you do to pinpoint the causal inference is vital, because in this, you have to kind of infer, basically, if you have been punishing me, what's the causal of that and how do I react to that? Because we don't only react to the action, but we infer the intention behind the action, and then we then act on it. So in this sense, but I think the different, so I've been thinking about this is that first you show that basically these language models, they are pretty bad at making causal inferences, right? And then you try to basically teach them the things we have learned as human beings on studying causality, and they do get better. And then on top of that is that we do social science, and it's super tricky to study causality. You know, we work with economics and then how much people just fuss over if it's 0.1 or 0.2 or 0. Like these kind of things.
Yeah.
So I'm just wondering, to what extent you think you can actually manage to do this with LLMs, and they actually can get the fine difference between every time when we do interact with each other as humans, and we make a lot of causal inferences of behaviors and intentions and stuff, and then on top of that, we then make a intent, like attitude, value, all of these steps. And then how I almost feel it's almost impossible to have them to be so complicated as a human, and then they can interact in a way that can truly reflect the human society. And I'm just wondering what's your thought on that?
Right. So I think this second branch of human society simulation is really, there is a very long way to go. And then the first study of, I don't know, a binary thing, this is a cause, this is a fact, tell me whether they're significant. I think we can reach textbook level, like what a physics teacher can teach you relatively soon. And then to reach winning the reviewer level, it's more also a little bit about human interactions there too. And a community specific bias on how to do this study. So that's yet to be fine-tuned. this like human society is very, very far reaching and probably only small scale interview simulation can be done. But large scale realistic simulation, we still need a long way to go.
Because you mentioned that we can make the internet even, I mean, that would be fantastic, I mean,
Yeah.
there are a lot that you can do with the younger generation, you will be more and more embedded in a reality that's different from how
Yeah.
we grew up, and then if you could do it beforehand, you can kind of see how things could go for them.
Right, yeah, and you can let an agent simulate a social media account of a simulated teenager and compare it with a real account.
Yes,
Yeah.
that's what we have been really thinking about doing, I mean, if there's some practicality in it, it would be awesome.
Amazing.
Yes.
Wow, exciting. I'm glad we have such a rich set of audience and happy to chat more soon. Yes.
They will come back throughout this week, next week.